Hi, my name is Stacy Thibodeau. I teach chemistry over in South Louisiana at Southside High School. And today I just wanted to share with you some of the activities that I do with my students in my chemistry classroom, as well as my robotics classroom, where we ramp up STEM data collection in your classroom. So, here's my contact information. If you have questions after this session today, you want to find out more information how I use TI technology, that's my information, as well as Twitter. I believe in promoting what we do in the classroom, especially when it comes to STEM learning. So if you want to follow me and I'll follow you back and we can share ideas. The QR code is there. This is a wealth of information in this document. If for some reason you missed it, I can send it to you as well. So why STEM? Why do I spend time instead of teaching chemistry? And why do I have a robotics class? Well, the main thing is to get our students ready for the future. If we aren't preparing them for the job market that's out there, then we're doing a disservice. So if we look at the number of jobs that are going to be computing, teaching coding and teaching programming skills in the science and or STEM classrooms is very, very beneficial for our students. So as a chemistry teacher, I have to follow standards. And so a couple of years ago, Louisiana adopted new standards. They are NGSS like. They're not NGSS, but they are NGSS like. And so I still have to meet the standards of the state as well as the district. And so how do I take a STEM project or STEM concept in the science, engineering, mathematics field and put it into my science classroom? So this would be a really good one to do in a biology classroom for this standard, but you could put it into a chemistry classroom. And so this standard is to develop and use a model about interacting systems within multicellular organisms. And you're like, Stacey, how are you going to build a model? Just wait. So in my district, we follow the 5E model of instruction. And so I'm going to just kind of walk you through a sample lesson of how I do it in my classroom. It doesn't mean that that's how you have to do it, but it's just how my mind works. So we're going to start off with an engage. So this engage is going to be a phenomenon. So I make my lessons phenomena based. And so a phenomenon in this case would be someone sweating. And here in South Louisiana, we do that a lot. So why do we sweat? Conversation you can have with students, maybe show them a picture, a video, image, whatever, and then have them create the driving questions for the class. Why do we sweat? What's the temperature at which we start sweating? What triggers our body to sweat? Is it always temperature? Maybe it's nerves, maybe it's anxiety. And then can we create a model that can demonstrate what happens? And so what we're going to do today is create a model for that. And our model is going to engage in this whole action effect feedback loop, feedback mechanism of a cross-cutting concept. And so this image helps to guide students into conversation. And so when you have normal body temperature that falls below a threshold, our body does something in response to that to bring it back to the normal temperature. If our body increases in temperature too much, your body's going to do something to bring it back. So feedback and control. We do this all the time without even thinking about it. And so what we're going to do is build a model using a temperature sensor, some temperature data, and then based on that data, create a model that has some type of feedback and control to demonstrate what happens when we sweat. So data collection, why do we need it? Why do we do it? Well, for one, it meets a lot of our science and engineering practices, but two, that's how students work. That's how their minds work. Students come to us with a wealth of science knowledge. We just have to know how to tap into that and lead them into these investigations where they ask questions, where they look at and analyze their own data, where they plan and carry out investigations, and then come back and have some type of argument of their data, and then with evidence maybe from literature or research. So in my classroom, I use the TI-Nspire CXs, and I also have a variety of different veneer sensors. And so these veneer sensors can plug into a lab cradle or directly into the handheld itself. So I don't have bulky computers all over my desks. I have my calculator and my sensor, and we're able to get data collection done real quick. And it's fast. What normally might take a long time to set up, there are a lot of shortcuts you can do with 30-second data collection or 1-minute data collection where you can get the gist of what you're trying to accomplish. So for this activity, what I did was I connected a temperature sensor, a stainless steel temperature sensor, to my teacher computer, which has my teacher TI-Nspire premium software, and I just collected some raw data. And so you're probably like, Stacey, that doesn't look very good. I just held it in my hand and I got a graph that increases. Well, it doesn't really matter if it's very good data because it's my data. And for students, if we can get them collecting their data, then they become the owners, and it's no longer about what Ms. Thibodeau thinks should happen in the classroom, but now the lab data collection is centered around the students' data, and they want to find more. So this picture is of the TI-Nspire software. Like I said, it's the lab view of a data collection. And so I'm able to see a graph. I can see a data table if I wanted to have students write down a data table. I don't have to, but the data table is there, so I can go through it and scroll it up. But then I can also have a conversation just with the graph. Maybe I don't have enough calculators or sensors for each student to use. I can plug it into my computer, collect data, and then we can still have this whole class conversation. Mathematical models. If we can get students to think and collect their data and then make mathematical models about their data, we're preparing them for all their standardized tests. So what's the rate of change? And so we would have a conversation that as 60 seconds pass, well, that's our X. And then the temperature change was about 11.1 degrees Celsius. So what is the rate of change or the slope? They know it's rise over run. So this is temperature over time, degrees Celsius over seconds. And we can calculate this real quick and easy and dirty with our y-intercept and come up with an equation of the line. So we're going to say the equation of my line was about 0.185x plus 27.5. Well, the software can actually draw and define the linear regression for you, the actual mathematical model. And if we look at this, my model wasn't all that off just with conversations that are happening with the students. And so you're like, Stacey, why are you having this conversation? Well, now students can use this temperature data to then go build their model of when they think it's important to sweat. We could have them build a model as far as drawing of the person sweating. What's the lowest temperature on the graph? What's the highest? It just depends what you want to accomplish from this. And then they're going to take that information and determine, why do we sweat? What's the temperature? And then they're going to set the program for all this, for this cooling or feedback mechanism. So the actual design challenge is, the engineering design part is to build a model system that uses temperature data from their lab we just did. That's the input. To turn on a warning. Okay, so we're not going to make sweat come out or drip or whatever, not a pump, but we're just going to turn on a sound and have a color display when that individual would be sweating. Maybe you wanted to change it. Maybe you wanted to add a pump. Maybe you wanted to add a motor to it for a fan to cool off, whatever. I just did this for you guys. And so, yes, I do spend some time talking about engineering design. A lot of students think engineers are these people that just work, in construction or whatever. So we talk about the design process, that it's very similar to what we do in science, where we try something, it doesn't work, we remodel and we come back to it. And so there's this entire cycle of trying and retrying. So I mentioned to you guys that I'm a chemistry teacher. And so I got started with programming and coding because I started using the TI technology. And so I didn't have a background, and I still don't have a background in programming or coding, but TI makes it user-friendly and easy for people to spend time away from students and then come back with the students and have successes. And so what this is over here on the left-hand side is the TI Innovator Hub, and I'm going to show you in a minute. And so that is our microcontroller, microprocessor. And there's in and out ports. And so today we're going to use an input, which will be a sensor. I could have put a fan or a motor or something on the output based on the data. So the coding programs actually work on the Nspire and the 84s. I have Nspires in my classroom, so that's what I'm going to demonstrate with you today, but it does work on the 84 Cs. And then this bottom picture over here is the TI Innovator Rover. And so it's a kind of on-ramp robotics, and so that's kind of what we're using in my class this year for robotics. A little bit about the Innovator Hub. The ports, like I mentioned, there's in and out ports. There is a breadboard connector, so if you want to add the electronics connections behind it, you could add that. There's an I2C port, which is used for our rover. There's mini USB ports, there's power ports, lights, and there's also a speaker, and that's what we're going to use today. And so you're like, how do I start? Well, that's not for me. I don't know how to program, how to code. Well, Texas Instruments makes it very easy for a brand new user to learn how to use it. They have what's called 10 minutes of code, and that is what I started with. I took my rover and my hub, started with the hub, took the 10 minutes of code and followed it step by step by step. And so learning how to do it before I went and used it with students was very helpful because I could show them how I troubleshooted through some of the learning process. And then I took what was in the 10 minutes of code and made projects for my students. There are STEM projects that are out there already, and there's a link to it right here, and I'll show you the link at the end. That there's different types of projects, kind of where I got the idea for this. And then there's some with anatomy, there's some with physics, there's some with using the rover, so a lot of different projects out there. And then also the website, I did put a link here. That way, if you want to find more information about the programs, you can see that. So what it looks like when you're programming with the hub is that it's what's called menu driven. And so the program is already there in the menu. You just have to figure out and then find the lines of code that you're interested in. Because most of what we're doing today is going to be through the hub. So when we click on menu, we can see there's a hub menu, submenu. And then these are the main ones that we can do that we would talk about today. Send, set, read, settings, connect other outputs or inputs. We're going to connect the vernier sensor today. And then I also have the colors selected so I can have a color and I have a sound for when my alarm needs to go off based on the temperature. I'm going to use what's called the sensor link. And I was so excited when this came about because I finally felt like I could use data collection that I had been doing in my classroom and tie it into the hub and STEM and kind of mesh them together. So the sensor link does just that. It takes your vernier sensors and allows for a plug-in and a link to the hub so that you can apply this vernier sensor data to a program. And currently it's the stainless steel temperature probe, a pH sensor, a dual range force, and a gas pressure sensor. And so what students are going to do for this project is just what I said. They're going to use the data that was collected from the original temperature data as the threshold. What temperature do you want for X? And then based on it, maybe you turn a fan on, like I said, maybe you have a pump, maybe you just have lights and sounds of when the temperature has been reached, and then you can have a conversation of what you would like to design based on that. So let me show you. And so here is my calculator, my handheld. This is the Innovator Hub. It's upside down because of the way the cables are. And I have into an in port the sensor link, also upside down because of the way it is. And the sensor link is connected to a temperature probe. And so I'm going to hold the temperature probe in my hand to simulate a hot environment. And I'm going to run the program. And my hand must be really hot because it immediately noted that it was hot. I have a light that came on, a sound that came on. There's also a display. I know it's hard to see, but the display says it's too hot, cool off. And so we could have set this to do whatever we wanted with the program. So that's my setup. Let me show you a little bit of what the actual program looks like. And so this was all menu driven. I went to the menu of the calculator and found how to connect the vernier sensor. I have some contact here that if I press escape, the program would stop. So it reads the sensor, and it's going to display the temperature. And then based on the parameters that I collected the data and what I think is going to happen in my model, if the temperature is greater than 65, then it's too hot. I'm going to set the color, in this case, to red. This is a red, green, blue LED. Then I set the time for a sound. If it's not greater than 65 and it's in between 50 and 65, it's just right. I'm not going to sweat. I'm not going to do anything. The color is green and the sound is different. But if it's less than 50, it's too cool. The color changes, the sound changes, time changes, and so on. And so it just allows the user to have fun with this, have fun and create programs, have fun and create projects. You could add engineering design component. Maybe you want to have students present their projects and some kind of evaluation that we're the sharks. And so my students have what's called the shark tank, where they present their information to the older students. And then the students decide who has the better of the projects. Just something to have some pride and ownership in their project. Other projects that you could possibly do that I'm going to do this year with my students, maybe use the gas pressure sensor. So we know in chemistry and chemical engineering, gas pressure can build up and it can change and it can cause a big explosion if we don't know about it. And so maybe instead of the temperature sensor, we're measuring the pressure, the gas pressure, and then based on the pressure of the gas, we turn an alarm on, we make color. pH sensor, which is my favorite. So there's two things you could do with the pH sensor. You could take the red, green, blue LED and match the color scheme like litmus paper. And then based on the pH value that the pH sensor picks up, you can make the light come on that color. I think that one's going to be really fun this year. Or you have an alarm, very similar to what we did with this one, that our alarm makes a signal when the pH falls too low or too high. And then I did mention that I would show you the website where there's more STEM projects. Let me click on that. And so these are tried and true activities. I've done all of these myself, whether I was at conferences or working with students, and different ones to start. So I would probably start with 10 minutes of code, and I'll show you where that is, to just start with the programming and understanding. This digital mood ring is probably one of the quickest ones to do. It has a temperature sensor, and basically based on the temperature, your LED turns a different color. Dog Days is a cool project where students are designing a alarm and mechanism for a car that gets too hot and there's an animal inside. And so the windows open and the lights flash and you can make the horn bump if you want. Here's the one I was talking about that's human anatomy or biology, and it's modeling a 4-chambered heart with lights to kind of show the flow of the heart. There's some on music. For the 10 minutes of code, if you come under activities, innovator lessons, this is the actual website with the lessons for all the different types of things. Here's the 10 minutes of code. And so based on the technology you're using, and we're going to go over here for the hub and rover 10 minutes of code. And then based on the technology you're using, it allows you to have the lessons where you could do it with your students. This year I have a robotics class for the first time. I have a whole year to teach it to them. So we did 1 week, unit 1. This week we're on unit 2. Next week we're going to be on unit 3. And then we're going to learn how to build it and add projects to it. So I hope you guys enjoyed this. Please feel free to reach out if you need anything, either from the ETC or myself. I'll be more than happy to have conversations with you about future projects, or maybe you just want to collaborate on something. Take care.